Hey everyone, welcome back. In this video, we're going to kind of continue this idea of working with line integrals, and we're going to use some similar techniques from that to be able to integrate over a curve that's located in a vector field. So in this particular instance, so we're looking at an integral for a curve, and our curve is laying in, like I said, in a vector field. And the way that we express this notion of figuring out what's happening with this curve in the vector field is to take integral over f dotted with dr, where r is kind of a representation of the parameterization of the curve. And as you might be able to kind of guess from how our last video went, looking at it set up like this isn't necessarily super informative, but there is a way that we can talk about this that makes it a lot easier to integrate. And that is going to be to use the expression of the integral from a to b of our vector field evaluated at a parameterization for our curve C, which is that r of t, and then dotted with r prime of t dt. So this really looks quite similar to what we did previously with our line integrals, except this time we have a vector field, which is at each point it's a vector, and that has to be dotted with the derivative of our parameterization for the line. So just to kind of label what's going on here, this piece right here, r of t, is the parameterization of our curve C. And to kind of interpret a little bit maybe more intuitively what this is actually telling us, what this integral tells us, is that we're kind of chopping up our line in little pieces, which is what this dt and maybe like that dr kind of represents. And for each one of those little pieces, what we're doing is saying, okay, let's look at the vector field restricted to the curve. And see how this curve is changing. And then by taking the dot product between those two things, we can see what they have in common. And then by taking, oops, common has two m's in it. And then by taking the integral from a to b, we're able to kind of add up each of those little effects at each of those little pieces in our curve. So it kind of gives you an overall notion of how our curve is interacting with the space that it is in. And this winds up being really useful for computing things like working with work or energy and things like that. So it has a lot of applications in physics and a lot of other fields. So let's go ahead and jump in with some examples. In all of these, we will be integrating the given non-conservative vector field F on the given curve C. And I say non-conservative because I'm actually going to do conservative vector fields in my next video, and you'll see why those get treated separately when we talk about that in more detail then. But the main idea right now is that conservative vector fields have some really nice properties that we're able to exploit in integrals. So we're going to focus mostly on the tricks for working with non-conservative vector fields in this one, because that's where we get this equation here from. So let's go ahead and jump into those. Our first example is going to be our vector field equal to y0, and C is going to be our line segments from 0, 0 to 1, 1. And in order to be able to look at this integral, we want the integral over the curve of f dot dr is how we express that. And that is equal to the integral from a to b of our vector field F evaluated at r of t dotted with r prime of t dt. So just like in working with line integrals in general, the first thing that we want to do is find this parameterization for our curve. So in this particular instance, we're looking at a line segment, so our parameterization has to be something of the form of a base point plus t times some vector moving from one point to the other. And in this particular instance, our base point p is going to be at the first point we start at 0, 0, and then v is just equal to, I guess we can call it pq. And that's just the vector 1, 1. Oops, like so. So r of t winds up being 0, 0 plus t times 1, 1, which is simply equal to t, t. So to get the derivative, we just take the derivative of each component here. So that's equal to 1, 1. And we also note that this right here means this line that r of t is equal to tt means that x has to be equal to t, y has to be equal to t as well. So if we wanted to write out this piece right here, f of r of t, there we go, that has to be equal to, well, we have t0 for that there. And finally, we recall that the bounds on t are between 0 and 1 because we are working with a line segment that starts at 0 and ends at 1, 1. So, all right, I think that's everything. We have all the pieces for our integral right here. So our integral over the curve f dot dr has to be equal to the integral from 0 to 1. F of r of t is t0, and then r prime of t is 1, 1, and we're taking the dot product of those two things right there, dt. Before we can integrate anything, we do have to compute that dot product. So we're going to get, it's actually just going to be t because we wind up with t times 1 plus 0 times 1. So that's just t dt. And that integral from 0 to 1 of t is equal to 1/2. And yeah, that's actually really all there is to it. It's not, it's pretty straightforward. It's not too bad. So let's look at a slightly more complicated example though. Okay, so in this one, we're actually going to have the same vector field, oops, 0, and then our line segment this time is going to actually be, or our line segment, our curve is actually going to be two line segments put together. So we have the line segment from 0, 0 to 1, 0, followed by the line segments from 1, 0 to 1, 1. And since we've got all these points running around, I'm going to go ahead and label them. I'll call this first one P. The second one will be Q. And I guess that one is therefore then Q as well. And so this last one will be R. Okay. So C is two pieces together because we have the first line segment and then the second line segment. So C is equal to two pieces put together. C1, we can call the first one, and C2. And, but we still want to kind of use our main formula, but we just have to break it up into two pieces. So the idea here is we have integral over the curve, f dot dr is equal to the integral over C1, f dot dr, plus the integral over C2, f dot dr. And, but we, again, still want to use our formula, integral over C f dot dr equal to integral a to b of f of r of t dot r prime of t dt, where r of t is really just the parameterization for each one of those. So we're going to have two pieces, compute them separately, add them back together. Same idea as we did with the line integrals earlier. So let's work with this first piece here. C1. So in this particular instance here, we're going from 0, 0 to 1, 0. So r of t is equal to 0, 0 plus t times 1, 0, where t is between 0 and 1. So I'm going to rewrite this. I'm going to get t0, which means that x has to be equal to t and y has to be equal to 0. And it also means that when I take my derivative, I'm going to get 1, 0. All right. F equal to y0 is now going to become f, oops, a little vector over that, equal to 0, 0. So the integral over C1 of f dot dr has to be equal to, our bounds were 0 to 1. Looking at f of r of t, that's this piece right here. So 0, 0, dotted with r prime of t, which is 1, 0, dt. And first, we got to take the dot product, and I'm just going to get 0 out of that because the 0 vector dotted with anything gives you 0. And then integral over 0 is just, well, it's 0. So that's all there is to finding C1. Okay, so that's my answer for this piece right here. Okay, so now we have to work with C2. In this case, we have r of t equal to 1, 0 plus t times 0, 1. And this is because we're going from 1, 0 to 1, 1. So 1t is what you get out of that. And this means then that x has to be equal to 1, y has to be equal to t. And we take our derivative for the second piece there. We get 0, 1. And then our f equal to y0 becomes, so if we have f evaluated at r of t, that has to be equal to, well, the t is going to go in for y, so I'm going to get t0. And then, I guess I didn't say this, but 0 less than or equal to t less than or equal to 1 still holds. Okay, so now we're ready to plug everything into our formula because we were still going for this setup right here. So our integral over C2 f dot dr is equal to the integral from a to b. Oops, well, we already said a to b. Let's do 0 to 1 of t0 dotted with r prime of t. So that's going to be 0, 1 dt. So now I have the integral from 0 to 1 of t times 0 is going to be 0. Plus, well, 0 times 1 is 0, 2. So integral over 0 again, which just gives me 0. So that was my second component. This means then that my integral over the whole curve of f dot dr, which was equal to the integral over C1 f dot dr plus the integral over C2 f dot dr is equal to, well, just 0. And yeah, that's pretty much all there is to that. We just had to break it down into a couple of different pieces, find the pieces separately, add them together. Same deal as with, I mean, they're really just line integrals all over again. We're just kind of changing up the type of formula that we plug into it. So yeah. Let's look at an example that has maybe a more interesting parameterization to it. In this one, we're going to have that our vector field is equal to y squared x, and our curve this time is going to be the piece of x squared plus y squared equal to 4, and it's going to be in the first quadrant, and it will have counter clockwise orientation. Okay. So, I mean, like, regardless of what the curve looks like and what our vector field looks like, first and foremost, the formula that we are working with is to be able to find this integral, we have the integral over the curve f dot dr has to be equal to the integral from a to b of f of r of t dotted with r prime of t dt. Okay, so that means that the first thing we have to do is find the parameterization for this portion of a circle. So in order to be able to do that, I think that this one, it's probably wise to start with a sketch. I mean, a circle sounds maybe kind of simple, and I mean, I guess there really isn't probably that much to it, but I find it really helpful to start with a sketch of this one because it's more complicated than a line segment. So, I mean, like maybe a good rule of thumb would be if you have something that's more than a line segment, sketching it might not be a bad idea. So, or at least if it's on the plane and stuff like that and nice to work with. So if we kind of sketch it, I'm going to get radius 2 because of that 4 right there. And it's in the first quadrant, so it's this segment like so. And we're told that it has counterclockwise orientation, which means we're going this way. Okay. And that counterclockwise orientation gives us information about endpoints of our curve. Well, the parameterization for a circle with radius 2, that's going to be r of t equal to, and this is the other thing, since it's a counterclockwise orientation, we want to use x going to cosine and y going to sine, as we typically would. So 2 cosine of t and then 2 sine of t. And then our derivative has to be equal to negative 2 sine of t and then 2 cosine of t. Okay. So this piece is equal to x. This piece is equal to y. And it's really important that you're keeping track of r versus r prime and what x and y are, because now we're going to want to plug into f. Okay, we want to figure out what is going to get plugged into our vector field here. So f of xy is equal to y squared x, which means that f of r of t is equal to, well, it's very easy to, and this is, it's just, you know, it's a silly mistake. Everybody makes it. I myself am guilty of this. It's very easy to kind of look back up and be like, oh, r. That's going to be what I'm going to use to make my substitution. Well, this is actually r prime, and it's very easy to just, you know, not paying attention, look at the wrong line. So I like to try to kind of label what I'm working with as much as possible so I don't accidentally misread something. So it's just a good way to not lose some easy points on like an exam or something like that, is just, and I mean, obviously also wind up with the right answer. Just make sure that you're reading off the right line here, that you're going back up far enough here to make sure you got from r of t. And then the other thing is here too, is that we've got the y and the x component and the x and the y component. So it's even easier to get things further turned around. Anyway, all of that aside, we're going to have 4 sine squared t and 2 cosine t as my new vector field. So yeah, okay. And then the only thing we're missing now are going to be bounds on t. And the way that we determine those is by looking at this picture here. So since we have the counterclockwise orientation and we're starting here and going up to here, t is going to start down here at 0, and then it's going to come up here to pi over 2. Anytime that you're working with like a circle or an ellipse, you should automatically think with your parameterization now as being like an angle here on the unit circle. So yeah. So t has to be between 0 and pi over 2. All right, let's start plugging things in. So we have our integral over the curve of f dot dr equal to the integral from 0 to pi over 2 of 4 sine squared t, 2 cosine t, and then dotted with, this is a dot product here, negative 2 sine of t, 2 cosine of t, because that's our derivative of r. And before you can take your derivative, you have to do the dot product. We're going to get negative 8 sine cubed t plus 4 cosine squared t dt. So yeah, that's pretty much it. That's all you got to do to set up the integral. Now to actually integrate this thing, it's fairly straightforward. The only thing you have to do is maybe look up a power reduction formula for trig, but those are, again, pretty straightforward to use, just a lot of plug and chug. So yeah, that's pretty much it. You just take this and you re-express it using that parameterization, and then you go through and plug everything in and do the integral as normal. So yeah. Oh, and I guess that's actually our last example for this video. So that kind of wraps up at least this introduction to working with integration over a vector field. In my next video, I'm going to highlight this idea of why we like conservative vector fields so much, what some of their useful properties are in terms of integrals, and how we can kind of actually create some shortcuts for this whole process when we have a conservative vector field. So yeah, I'll see you guys next time when we talk about why conservative vector fields are so great. So see you then.